Hi, I'd like to welcome everyone to this edition of Gauge Theory Virtual. We're pleased to have Andriy Haydys with us, presenting on the blow-up set for Seiberg-Witten equations with two spinors. I will let him take it away.
Okay, thank you very much. Thank you for this opportunity to give a talk here. So I will talk today about the blow-up set for the Seiberg-Witten equations with two spinors, which may sound a bit odd. So the combination of the Seiberg-Witten equations and the blow-up set. So let me explain first what is meant here. So I start with a closed, oriented, and Riemannian string manifold. And such a manifold is spin, so let me choose a spin bundle. So this will be denoted as, and this is a spinor bundle. And also let me choose a Hermitian line bundle. This is Hermitian line bundle, and I will take also, I will take a connection on this Hermitian line bundle, so a Hermitian connection. And the equations that I want to consider for today look precisely at the classical Seiberg-Witten equations. That is, we have a harmonic spinor, and we have the curvature of the connection on the line bundle equals to the quadratic expression in psi. The only sort of unusual thing is, so I'll think of mu of psi as a one form. But anyway, so capital psi here is a section of the spinor bundle twisted by the line bundle. So this is my spin C bundle, and in addition, I will twist this by a product, so the product bundle of rank 2. And sometimes it will be convenient to think of this as a space of sections of homomorphisms from C2 into S tensor L. In any case, so what is then mu of psi? This is so if you think of psi as consisting of two spinors, say psi 1 and psi 2, then the right-hand side here is, the classical quadratic map of the first spinor plus the same quadratic map applied to the second spinor. So if you wish explicitly, this is psi 1 dual minus 1/2 the absolute value of psi 1 plus psi 2 dual minus 1/2 absolute value of psi 2 squared. Or in terms of capital psi, this is just psi dual minus 1/2 norm of psi squared. So in any case, this can be interpreted as a one form exactly as in the classical setting of the Seiberg-Witten equations, and so the equations do make sense. But one important difference is that the map mu, which appears here, is not actually proper, as in the case of just one spinor. And this actually gives that the proof of the compactness actually breaks down, which raises the question whether the moduli space is compact for this setting. But maybe something important that I should not forget is about this twisting bundle of rank 2. So here in this setting, I could have opted with any Hermitian vector bundle of rank 2. This is topologically, of course, trivial, so I do not lose anything here, but I could have equipped this with some extra connection, a Hermitian one, which is fixed in this setting. So I've chosen here to work with a product connection, but keep in mind that I could have started with any extra connection on this bond. In any case, with this understood, so the question we want to ask is whether the moduli space is compact, and an answer to this is given by the following theorem due to myself and Thomas Olkuski. So by now this is an old result. So the theorem is as follows. So let an psi n be any sequence of solutions to, let me call the equations SW2. So this is SW2. Then there are two cases. So the first case is if the sequence of L2 norms of psi n is bounded, then a subsequence of an psi n converges, possibly after applying gauge transformations. So that's pretty similar to what one has in the classical Zygote-Witten theory. More interesting is the following case. So assume that this sequence is unbounded. That is, if you take the L2 norms of the spinors and this diverges to infinity, then there exists a closed, nowhere dense subset set in M, such that the following holds. What we have is a subsequence of an. So you see, psi n diverges to infinity, so we don't have any chance to get something convergent unless we renormalize psi n. So that's what we do. Let us renormalize psi n so that it has norm 1, say in L2. And then a subsequence of this converges over the complement of that. So let me say converges to some a psi over the complement of that. And what can we say about a psi, about the limit? So a psi satisfies essentially the same equations, dA psi equals 0. And so here is a difference. We have only mu of psi equals 0, but we don't have the curvature part. And this holds over the complement of Z. And even the solution itself, a psi, is defined only on the complement of Z. And one more piece of information that we have is the following. So if you take the pointwise norm of psi, this extends as a continuous function to all of n, and the zero locus of this function is exactly that. Okay. So if there are no questions to this theorem, I will say that that is a blow-up set, and we'll be interested in the question what can be actually said about this blow-up set. Well, let me explain maybe first why I'm calling this a blow-up set. So what you should imagine is that if you take the sequence of energy density, so if you take the pointwise norm of the curvatures in the sequence FAN, of the curvatures of AN, what happens is you see something like a delta function along Z, and this is why it's called the blow-up set. Okay, now, so what this theorem actually suggests, maybe let me remark so what is new in this theorem is exactly this blow-up set and this behavior of sequences which diverge to infinity. So in any case, what this actually suggests is the following conjectural picture. So conjectural behavior of the moduli space. So from the setting I had, we have the moduli space of solutions. So there is a psi which solves SW2, and this is divided by the gauge group. So let's say C infinity M U1. So if you maybe I'll just draw the picture and then explain why I think this is actually the case. So the thing is that for a generic metric G on M, this moduli space is expected to be compact. Yes, compact. So it's a let me say a finite set. Schematically, if this denotes the space of all parameters in the problem. So the only parameter I have shown to you was the Riemannian metric, but you can imagine other parameters that you need to perturb the equation. So let me say space of all parameters. So say Riemannian matrix on M. So the space is conjecturally divided into a number of chambers by walls. So let's say something like this. And so if you pick one metric in one chamber, say G0, you have that the number of the solutions is actually well defined. So as locally constant function on if you denote I denote this space by saying R walls by W. So we have a locally constant function on R minus W. But if you cross walls, what happens is that this function may actually change. And so if you arrive in a different chamber, you will get a different value for this function. And so let me say this number MSW2, which depends on the one parameter family of metrics, say, may jump for finitely many points in the interval 0, 1. So why do I actually think this is true? This is because if you look at the limit problem that we've got in this theorem, so let me note this maybe by SW2 0. This turns out to be, so at least in the case when Z is smooth, this turns out to be a Fredholm problem of index 0. But there is a natural scaling in the problem. So whenever you have one solution, you have the whole one parameter family of solutions. And this actually means that even though the index is 0, but actually you will see solutions in a codimension, on a codimension 1 subset. So what I'm talking now is everything is conjectural. So that's why you don't, presumably you don't have solutions of the limiting problem, which forces the moduli space to be compact. But if you consider, the moduli space in one parameter families, at some points you will see solutions to the limiting problem, and that's where the jump actually may occur. And unlike in the classical Zyber-Clipping theory, we don't expect to have an invariant of 3 manifolds, and the natural question is, why do I actually care about this? And the answer to that question is that this jumping behavior is actually something that we were interested in when we started the project, and namely, so this is conjecturally, so conjecturally this can be used to produce invariants of compact G2 manifolds. So let me just say that G2 manifolds are seven-dimensional manifolds with very special metric on them. And I don't quite want to go into details what is the relation between this gauge theory in dimension 3 and manifolds in dimension 7. This would be worth its own talk, but that's actually where the motivation for the whole project comes from. In any case, so as I said, I don't want to go into details, but the main question for today will be what can be said about the blow-up set Z. So a midterm goal here is to prove that this picture that I sketched for you, that you have the space of parameters which is divided by walls into chambers, is actually true. But to prove this, we need to understand this blow-up set Z much better than we understand now, and this is sort of a report on the progress in this direction. Okay. Now, the first observation is that if the twisting Hermitian line bundle, so if squared, that is, if the determinant line bundle is non-trivial, and the moduli space of solutions is non-compact, then actually Z is non-empty. So you see, even though we have this possibility in the theorem I formulated to you, but actually you may have thought that maybe this is just a deficiency of the proofs, that we get some set where we just can't prove the convergence. But maybe this set shouldn't be in the theorem. So what I'm claiming is that this is an essential ingredient of that theorem. So let us understand why this is actually so, since the argument is essentially elementary. So if you know that the moduli space of solutions is non-compact, then this means that there exists a solution, say A psi set of the limiting problem. And if you assume that, so assume the corresponding blow-up set is actually empty, then what we know is that a psi is well defined on the all of M, and we know that mu of psi is 0, and so by definition this is just psi dual minus, well, let me say this is just the same as saying that this is equal to 1/2 norm of psi squared, which is assumed to be nowhere vanishing. But saying that this is nowhere vanishing implies that the kernel of psi dual is 0, right? Which is to say that psi is surjective. But now, so recall that psi is a homomorphism from C2 into S tensor L. So this, the source is of rank 2, the target is of rank 2, and in fact, then this is an isomorphism. And so if you take the determinant of psi, you will obtain that lambda 2 C2, which is of course just the trivial line, is isomorphic to lambda 2 S tensor L, but this is L squared. And so what we get is that the determinant line bundle is trivial, but we assume that L squared is actually non-trivial. So whenever we have a species structure where the determinant bundle is non-trivial, then we know that the moduli space is non-compact, and this blow-up set must be there, and it's non-trivial. But of course, you can ask now, do we actually have examples where the moduli space is non-compact? And in fact, we do, and pretty explicit examples. So for that, what I will do, I will take the following twist. So I will think of C2 of the twisting bundle as being a copy of the spinor bundle itself, and this will be equipped with the latitude connection. And so my spinor will be a section of the bundle of homomorphisms, so from S to S tensor L, and well, this is just and S tensor L, but the endomorphisms of the spinor bundle are just one forms, so this is T star M complexified tensor L plus L itself. So in essence, we have one forms twisted by L, and proposition due to myself, quite a recent result is that there exists a one-to-one correspondence between MSW2, between the moduli space of solutions with this particular twist and flat stable PSL to R connections. So I don't want to explain what stability here means. Let me just note that whenever you have a representation of the fundamental group of M into PSL to R, which is irreducible, so let me say each irreducible is stable in that sense. And since it's it's easy to construct examples of street manifolds where the representation variety is non-compact, so we have pretty explicit examples of non-compact moduli spaces of solutions to the Seiberg-Witten equations with two spinors. And therefore, we also know that this blow-up behavior actually does happen. Even though, so up to now, we have almost no examples of solutions to the limiting problem. Okay, so if there are no questions to that, let me return to the questions that I posed earlier. So what can I say about this blow-up set Z? And there are many ways you can answer that question. So the most basic question is about the regularity. So the best known result up to now is the following theorem due to Bouyou-Chan, which says that Z is one rectifiable for any metric G. So one rectifiable here means, roughly speaking, the following. So the dimension of Z is 1, so the Hausdorff dimension, and the length of Z can be defined and is finite. So we have something like a curve which may have singularities, so we don't know where the singularities are, how they look like, but what we know is that the total length of singular points is 0. If you don't know what one rectifiable is, you should think of this saying as you have something like a curve, but this curve may be singular. And in fact, quite recent work by Taubes and Wu actually produced first models of singularities. So local models of singularities of Z. So it seems that for general metric G, we may have a singular blow-up set, which is probably not that surprising, but actually what I conjecture, so that's not really my conjecture, something which circulates among people working in the field, is that for generic G, any blow-up set is actually smooth. So by this, I mean that is a link in N. So at this moment, we are pretty far from proving this conjecture. It's not, there are many problems which need to be solved for that. But that's, I think, where we are heading.
So Andriy, I know that you said for generic G, the expectation is that Z is, the expectation is that the modular space is compact. So then what do you mean by this? So for generic metric, you even don't have a Z, right?
You're absolutely right. So I'm not terribly precise here. So what I mean is this. Let me return to the picture I had at the beginning. So you're absolutely right. So for generic G, there shouldn't be any solution, and there shouldn't be any blow-up set. But what this means is that if you are, so there is a 4-dimension one wall where you expect, expect to see solutions, and for generic G in this wall, Z should be smooth.
I see. Don't take this too literally. So it's probably not true that you can achieve, a smoothness of Z just by perturbing the metric. You need other parameters. But I'm not, as I said, I'm not terribly precise here. Okay, but what I wanted to concentrate more on today are certain topological properties of these blow-up sets. So geometric restrictions on that. And so the first theorem I want to discuss is the following one. So if Z is a blow-up set for the Dirac-Witten equations with two spinors, with the fraction class of the determinant bundle being A, then that represents a homology class set in the first homology group of M set, such that it is Poincare dual to the fraction class of the determinant line bundle. So what I'm saying essentially is this: even though that is singular, and we don't quite know how singular this can be, nevertheless, the homology class of this set can be defined, this is such that it is essentially given by the fraction class of Poincare dual to the fraction class of the determinant line bundle.
Again, I'm not terribly precise here, so hopefully I will have time to present proof and I will make the statement more precise. But one particular corollary of that is that if the Fechtian class of the determinant bundle is non-trivial, then the total length of the blow-up set is bounded from below by a constant which depends on the metric and A only, and is strictly positive. So H1 here is technically the one-dimensional Hausdorff measure of Z, but we can understand this as a total length of Z. So this is and one more theorem that I want to discuss today is more recent result. So let me assume that M is an integral homology sphere. So if Z is smooth, so here I assume that Z is smooth. So let me say if Z is smooth, blow-up set for the Seiberg-Whitney equations with two spinors, and the twist that I mentioned once. So when E nabla E is equal to the spinor bundle with the Levi-Civita connection. So in the case where we have flat stable PSL to R connections, then so what we have is we have a link in an integral homology sphere, and I can take the Alexander polynomial of that link. I can evaluate this at the point -1, and I claim that this is non-dimensional. And here, as I said, this is the Alexander polynomial of Z. And in particular, what this gives us, that is an honest link, that is, it must have at least two connected components. Okay. Are there any questions to the theorems?
So,
Okay.
Andriy,
Yeah.
So the link, the set Z can be empty also, right? So does this apply to empty Z in any way?
Actually, I mean,
do you mean to say that that value is 0? That's what it says in the abstract.
Yeah, I think that something is not right.
in which theorem?
Well, what Tom is saying, I think, is that Alexander polynomial over naught at -1 is never equal to 0.
It is equal. It is equal to 0.
You might say probably it is 0.
It is 0.
Okay.
Yeah, that's absolutely correct. Thank you. All right. So then let me discuss briefly the proof of theorem A. So this proceeds in a number of steps. So the first step is the following. So this is essentially just a simple observation. So the observation is that there is a section S of a continuous section of the determinant line bundle such that Z is the zero locus of this section. And essentially, we have already seen the proof of that. So what we have is that psi is a section over M minus Z of on C2 S tensor L. So I can take the determinant of that map. Now this is a section of of home lambda 2 C2 to lambda 2 S tensor L, and this is trivial. This is L squared. So I have homomorphisms from the trivial bundle to L squared. So this is just a section of the determinant bundle. And the fact that mu of psi is 0 is to say that psi dual is 1/2 norm psi squared over M without Z, but over the complement of Z, this is non-zero. So the determinant is, so psi is isomorphism, and this means that the determinant of psi is non-zero. And since psi vanishes on Z, the determinant also vanishes, and so we have exactly a section which vanishes on Z. Now the second step in the proof is due to Taubes, and it says that for any point Z in Z, there exists a tangent cone, so let it be Z star, consisting of finitely many arrays. So what this means is the following. Assume this is Z, and let us look at a small neighborhood of a singularity of Z, or any point of Z. And if you zoom in, what you will see is a larger ball and a finite number of rays in that ball, maybe something like this. So that if you take a neighborhood of this collection of rays, then that will be contained somewhere in this neighborhood of this collection of rays. So the picture that I have here is in T Z M, so which is R3. Okay. Now, the next step is essentially an infinitesimal version of the previous step, or step 1. So the claim is that each tangent cone star in R3 is a zero locus of a map as star from R3 into C. And so what this gives is the following. So we can define weights and orientations on each tangent cone Z star as follows. So let us consider the tangent cones that we have, something like this. We know that we have a map. So pick one ray and say this is L. Now we can take a small loop which encircles this ray exactly once. So let it be gamma L, and I can take S star and consider this as a map from gamma L into C star. So 0 is not, so the zeros of S star are not on gamma L, and I can take the degree of this map. And let me denote this by theta L. Now this is not quite well defined because I didn't say what the orientation of the circle is, but if I take the absolute value, this is now well defined and is an integer. And whenever this integer is non-zero, I can also orient L so that L so that this degree is positive. And what this gives me is a huge collection of data which consists of all tangent cones to Z at all points, together with weights and orientations. And it turns out that this collection of data is enough to say what is the homology class of Z. The next step is a formal statement to that, is that for H1 is well defined. Now, how do you see this? So one can show is that if you have a set Z which has tangent cones at each point consisting of finitely many rays, then you can approximate Z. So that can be approximated by embedded graphs. G and these graphs, moreover, each approximation G can be equipped with a flow. So that or induces a flow on G. So maybe let me just tell you briefly what a flow is. So if we have an embedded graph, something like this, so if this is G, then a flow is a collection of orientations on edges and weights, something like on the picture.
And the requirement is that the sum of the weights of incoming edges at each vertex is the sum of outgoing edges. So something like on this picture. And so if you have a structure like this for an embedded graph, the homology class in M is well defined, and actually it turns out that this is independent of the approximation, so you can actually define the homology class of Z theta 4 to be the homology class of any approximation. So this finishes the proof and actually explains, the formulation, namely the homology class of the set itself is probably not well defined, or is not always well defined, but with this extra structure, so with infinitesimal weights and orientations, it becomes well defined. Are there any questions? Okay. Now, so let me prove the corollary. So, proof of corollary. So the corollary was that the total length of Z is bounded from below by a constant which depends on the metric G and the Hessian class of the determinant line bundle, provided A is non-zero. So I will define the CAG, say CGA, to be the infimum. What I take the total length of graphs G. So G is an embedded graph which admits a flow. So there exists a flow theta 4 on G such that G with this flow represents A. And I claim that this number is non-zero. So why is it so? If this infimum would be zero, then each connected component of the graph G would be contained in a small ball. But then in this case, the graph couldn't represent a non-trivial homology class. And so, therefore, it's positive. But since Z can be approximated by graphs, embedded graphs with this property, this implies that the total length of Z is also bounded by this constant CGA. Okay, and I still have a few minutes, so let me come to the proof of theorem P. So the statement was as follows. So M is an integral homology sphere, and Z is a link. In that case, we have that the Alexander polynomial at -1 equals 0. So the proof proceeds in a few steps. So step 1 is we have the limiting problem, dA psi equals 0 and mu of psi equals 0, and this is on the complement of Z.
So this property tells us actually that there is Z2 harmonic one form, let's say on the complement of Z. So this is a concept due to Taubes. So let me explain briefly what this actually means. This means the following. So on the complement of Z, there is a real line bundle. This is a real Euclidean line bundle I and omega, which is a one form again on the complement of Z, so that with values in this real line bundle, such that if you take the pointwise norm of omega, this extends as a continuous function to all of n, and the zero locus of this function is Z. There are some technical conditions also for omega that I don't want to mention, so it won't be that important. So what is important is that omega is harmonic, because that is d plus d star applied to omega is 0, and this is on the complement of Z. Okay. Now, next step is to take the double branch covering of M. So let it be pi. This is double branch covering of M. With double, let me say, double covering of M branch along Z. And so in that case, I claim that the first Betti number of M2 is actually at least 1. So why is it so? So if you take the pullback of omega, this is now an honest harmonic one form on M2, say without the preimage of Z. So this is harmonic one form, but this is not exactly smooth, but it's Lipschitz along the set where it's not defined. So this is Lipschitz, and for such forms, we do have an analog of Hodge theorem. Actually implies that the cohomology class of omega is well defined. Well, this you can see actually quite easy just from the very definition. But what is a non-trivial conclusion is that this class doesn't vanish. And so, in particular, this means that we have a non-trivial cohomology class on the double covering. So the first Betti number is, or the second Betti number, if you wish, is at least 1. And a topological fact is that the first Betti number of the double branch covering is at least 1. Actually implies that the Alexander polynomial evaluated at -1 is 0. In particular, if you have just a knot, so a one-component link, then if you take the double branch covering, then what you will get is a rational homology sphere. So this case actually never appears. And this finishes the proof, and that's all I wanted to tell you today. Thank you very much for your attention.
Oh, well, let's thank Andriy for a lovely talk. And if there are questions, now is a great time to ask them.
I have a question. Can you say a couple of words about the existence of the two harmonic form omega? How we derive it from the equations?
You mean this step where you have the equation,
Yes.
the solution of the limiting equations, and why is this two harmonic one form?
Yes. Mm-hmm. Is that Taub's result, you said?
Well, yes, you can interpret this as a Taub's result. What I told you is that in this particular twist that we are considering, where we take the spinor bundle as a twist.
Mm-hmm.
So we have a one form on the nose. So we have a flat, stable PSL to R connection. But this is a particular case of flat PSL to C connection, and so you can invoke Taub's result here if you wish. So Taub says, and in the limit we have as a two harmonic one form.
Okay, but is there a direct formula, explicit formula for omega?
Yeah, absolutely. So you can see this. So that's essentially an algebraic fact. So because I already passed to the limit here, I don't need actually to invoke Taub's result. But I just need a very little piece of Taub's argument, which says, maybe I will write here. So what I said is that psi is a section of on S tensor L, and so I can think of psi essentially as the one form on M without Z with values in L. And then the equations dA psi equals 0 and mu of psi equals 0 are just the same as saying that dA plus dA star applied to B equals 0, and write sigma B wedge B equals 0. So what is sigma? Sigma is just a real symplectic form on the fibers of L. Right, and so this equation actually, so the second one tells you that B takes values in some real sub-bundle in L, and so this gives you immediately that we have a Z2 form.
Okay, thank you.
So in the last step of the proof, you were working on the branch double cover, but the metric on the branch double cover was not a smooth metric. So the Hodge theorem still applies in that situation.
Yeah. So it's absolutely true that the metric is not smooth, but you can arrange the metric to be also Lipschitz. And there is a variant of the Hodge theorem for this setting, where you have a Lipschitz metric and a Lipschitz span form, and still, each cohomology class is represented by a harmonic one form. But that's correct. So I mean, it's not obvious. It's an sort of non-obvious ingredient of the proof.
But so you take the pullback of just the standard metric and underline. Okay.
So if you take the pullback of the standard metric, it's not good enough. You still have to modify this a little bit so that it is sort of behaves like a metric that is bounded along there. Let me say, so the local model for the double branch covering is C goes to C, Z goes to Z squared. So this map is actually not good enough. What you should take, I believe, so you should replace this by capital Pi, which maps Z to Z norm Z squared. So this map is slightly better behaved, and if you pull back the metric, it has the right behavior to apply, this variant of the Hodge theorem. Does make sense?
Yeah, I have to think more about that, but yeah, thank you. I also have another question related to this result, but can you, about the relation to flat PSL to R connections, can you comment on the proof of that? Like what goes in the proof?
I mean, not that much. That's you see, right. So again, so you have the spinor takes values in the bundle home as tensor L. Essentially here we have just a twisted Dirac operator which acts on 1 forms, or say on 0 plus 1 forms. But the Dirac operator which acts on forms is very well known, right? So dA will be written in this term as dA plus dA star. Right, and the only thing, well, not the only, but sort of the main thing to compute is this quadratic map which you apply to psi. So if you interpret psi if you interpret psi as a 1 form, then you can show that this quadratic expression is actually what I already written about. So this is sigma d wedge b, and that's more or less the only thing which needs to be computed. But that's not hard. So in a sense, there is no analysis involved in that computation.
I see. All right, thank you.
Sure. Well, you still need to show that this corresponds to flat PSL to R connections, but this is again an algebraic fact. So,
right.
Well, it's not a fact, it's an algebraic computation.
if there are no further questions, we can thank Andriy again. Of course, if there are, we can continue to ask.
Okay, thank you very much.